Hello and welcome to today's webinar. My name is David Cash. I'm a member of the marketing team here at Mountz, and I'm glad that you've taken the time to join us today as we look at our topic of 5 ways to improve process efficiencies and fastening automation workflows. Now, today's presentation has a really big or a really nice demo portion to that. So we'll get to that here fairly quickly, but I just wanted to let you know about that as we look at some of the ways that we can help to improve process control through the use of some of our tooling. Now, when we're looking at process control, repetition is something that we talk about and, repetition definitely is something that is an issue, and it can be an issue, especially if we're talking about fastening repetition. Because repetition is kind of a mundane process, it may be easy not to be fully engaged in that process. And in this case, that can cause errors, and those errors that happen during a fastening process could be errors of cross-thread events where the fastener binds up and the tool will clutch out, but the fastener is not fully seated. And then we are losing our clamp force for that fastener. It could be fasteners that are being missed totally. It could be fasteners that are partially run down but not fully seated. So there are those fastening issues that can come up because of repetition, and that waste of the actual product then turns into rework, which is another portion of waste. And if you are in the lean manufacturing world, you will see and understand what this graph means. So our dotted line that moves across the horizontal section there is our capacity for that product to be made. And that's going to be from the very beginning until the very end of that process. And so if we are at full capacity and everything is moving as it should, this is the line that we need to be at. But in reality, the wave line is what we typically see. And in this case, the distance between the lower portion and the upper portion of the curve is going to be our Murrah, or the difference between those two values. Everything below the line is our Murray, and this is things that have been overburdened or overworked, and that could be a result of people being overworked. It could be machinery that's overworked or backlogged. And so this is one area that we deal with. Everything above our capacity line is going to be our muda, which is the waste. And that could be the waste of transportation, moving apart from one area of the line to another area. It could be the waste of the actual physical product, or again, the rework. But this is typically when we're in that lean manufacturing, what we're looking to do is try to move those two curves closer to the capacity line so we are performing very, very well. And that's going to lead us to our poll question for today. It's a fairly simple one, very straightforward. But during your assembly process, when you're putting components in together, do those have more than one torque application during the process? I'll give you just a minute here to go ahead and answer that, and then we'll jump right back into the presentation. All right. So, as anticipated, the answer overwhelmingly was yes to that. And so, when should you consider workflow automations? So let's take a look at what some of those things that you might want to try to achieve by doing this. And that's going to be the repetitive series of fastening tasks, increasing production rates, increasing savings by possibly reducing tool costs. Also, we want to try to optimize workstation cycle times, improve product quality, and enhance process reliability, consistency, and efficiency. So these are some of the reasons why you may want to use some workflow automations. And these typically are also the benefits that we would see. Another benefit is that we are helping to remove the operator influence that may happen during the actual fastening process. And by doing this, we can also get data to analyze what may be happening and give us some more visibility about the actual operation that we are doing. Now, here are the 5 ways to improve efficiencies with workflows. Now, these can be done independently, but most likely they're done in conjunction with one another. And our first one, we kind of touched on it slightly, and that's going to be to error-proof the fastening process. Now, the Poke-Yoke philosophy of error-proofing is the opportunity given to the operator not to make a mistake. And we see this in everyday life, from trying to start a car. We must have our foot on the brake when we press the ignition to start the car. We also see it when we are pumping gas into our car. The nozzle must be fully inserted or the gas pump is not going to function. These types of behavioral changes give us the ability not to accidentally start our car in gear or spill gasoline all over the place as well. And so if we can add the error proofing to the fastening process, then we can ensure that we're getting the proper torque control that we're looking for, which is giving us the proper clamp force, which is what we actually are intended to have through the use of our torque, is the correct clamp force. And by doing this, this gives us the ability to not only have the proper torque control, but we're now introducing process control through the automation process, which also gives us real-time monitoring of the fastening process, giving us immediate feedback to the operator on what is happening with the application. And there are several items that we can use in this case to alert the operator if there is an issue. This also gives us the ability to integrate the tool itself into other line control devices, such as PLCs or things like that. But by error proofing the assembly process, this is one way that we can do that and give us the ability to control the process through that. Process or item number 2 is going to be to have automatic or automated data collection. And by doing this for the assembly process, this is going to give us the ability to have documentation of what's happening through the fastening process. And with that, we can then look at data-driven results to actually influence how we may proceed in whatever area we are looking to try to improve. And by looking at the fastening data, we can analyze different things, like we can look at how one operator compares to another operator. We can look at how one shift may compare to another shift. We can look at the results during days of the week, could be days of the month. Whatever items that you're looking for, you may be able to get information from the fastening data for you to make really good data-driven results for that. So if you have an automatic data collection ability, then that's going to give you that process with that. So our third item on our list here is going to be the ability to have transducerized smart electric screwdrivers. And basically what this means is we have a built-in sensor that's built into the tool that is constantly measuring the tool in real time. And so with that, that gives us the ability, again, to get instant feedback on what is happening with the tool, and allows us to have traceable and documentation of how that tool is performing over time. And we can also, use that information to see how the process may be working in the actual assembly that is happening. Our number four item is going to be process control. And basically, this is just a set of standard tasks. I'm going to need to learn to talk today. Tasks within the process. But what is nice about having process control around the fastening process is that we are able to program assembly sequences that are done for a specific fastener within that particular step. So that gives us the ability to have tolerance done for each fastener. And those tolerances can be based off of either the torque value, it could be the amount of angle that is run, it could be a number of different factors that we can control with the tool that allow us to be able to implement that in the process control during the fastening rundown. This allows us to do multiple fastening tasks and gives us the ability to be able to consolidate workstations if they have that ability to manage many different torque values and different types of fastening during that. So that would take, in this graphic here, we have 6 that are being condensed down to one workstation. And so finally, the fifth item here is our fastening automation. And basically this is the intelligent process of doing our fastening, which gives us the ability to replace manual processes for the actual assembly. And basically what this is meaning, it kind of ties in close with process control, but we're trying to eliminate steps that the operator has to go through to move on to a next step. And that in the fastening process could be changing the controller from one preset to another preset. It could be having maybe a cobot or something place a part while the operator is fastening, moving to the next operation. So these types of fastening automations can certainly help in increasing the efficiencies that we might be looking for. These types of items then can be digitally interlaced with other I/O interfaces, such as PLCs, line control devices. There could be light trees. They can also be integrated with locks or jigs. So the part can't be released until all of the fastening is done and that it's done correctly. So all of those areas give us the ability to control what's happening and giving us the ability to have nice automation for the process. And so if we recap all 5 of these areas, the first one is going to be to error-proof the fastening process. The next is auto data collection, or having that being able to be automatically captured. Using transducerized tools to be able to capture the real-time data from the actual torque values that are being generated by the tool. Implementing process controls where we can create assembly sequences, and finally we have the ability to have fastening automations excuse me, that allow us to be able to control what is happening during the fastening process. So that all of that we can get a good understanding of how we can use these principles in the use of a DC control tool to help with the operation workflows. So let's go ahead and jump into our demo section, and we're going to run through kind of a couple different scenarios so we can highlight different areas through the process. And so our first application scenarios are that we want to consolidate workstations, and that can be done and achieved fairly simply with the use of a DC tool. And this would be for possible line integration from systems that are using standard clutch tools across different multiple workstations, or they could be different lines that have different torque values, and we want to be able to consolidate those workstations. And so what we have here is the image of our controller. This is our EC TD Plus controller. And for us to be able to have that consolidation happen, we can do that by assigning different values to different presets throughout the tool itself. Now, on this model, we have 15 available presets. This is going to be expanding shortly this year, where we're going to be have the ability to have many more than 15. But currently, right now, there are 15 available presets. And then we also have two specialty presets, a multi-sequence A and a multi-sequence B. And these primarily deal with being able to stack different presets on top of each other for one rundown event. And these are typically going to be in scenarios where you may have a soft joint where you want to exercise that joint, or there could be some challenging aspects to what might be happening for that joint. So there are a couple of specialized solutions that we have that we can use in there. So doing that gives us the ability to have different, basically 15 different tools that we can utilize for our application. So our next scenario is we have a fastening bottleneck, and this could be due to the fact that we have a cycle time that we may need to increase, and it's because we have a fastener that has a lower torque value but a very long run time. And so if we take a look here at our thread block, we've got a couple different fasteners here. We'll be working primarily with these fasteners here, and we'll touch on the fasteners up front here for another scenario. But currently, right now, we have a preset that we're using, which is preset 13. We have a torque value at 2.5 Newton meters. But when we run this system down, we have learned that if we run much faster than this, because this is a delicate application, it causes inconsistencies in our torque value. And so if I go ahead and I run this down, you can see that it takes a little bit of time for us to be able to do that. So that's nearly 5.5 seconds for us to run this fastener down at about 6,300 degrees of rotation at our RPM speed of 200, which again gives us the correct clamp force and torque that we need for this section, or for this fastener. So we need to increase the cycle time because it is providing us with a bottleneck. So how can we go ahead and do this? Well, if we jump into our menu in here in our parameter section under this fastener, we'll go to fastener 13. We do have two items here that we can use to help to make this operation go a little bit quicker. The first one is going to be our free angle and our free speed RPM. And so this gives us the ability to turn the tool up to a faster RPM for a certain period of time, or excuse me, in this case, it's going to be the amount of turns. And we can do that right here. So in our free angle, we'll set this to, let's say, 5,000 degrees of rotation. And then we'll turn our RPM to the maximum at 690 degrees, or excuse me, 690 RPMs. And now this is going to allow us to run this fastener in a much more efficient manner. So if we come back out to our preset, again, preset 13, and let's go ahead and run this down. So you can see that we've brought that down to almost 2 seconds, and we've been able to basically more than double the speed that would have taken for this particular fastener by utilizing that feature within the DC tool. So that would be how we could handle that bottleneck for this application. Our next scenario is going to be a cross-thread type of issue. And how we can solve this is a couple different ways. And we'll show you both of them here as we move to the display. Let's move this up just a little bit so you can see that a little bit better. Go. All right, so if we head back into the controller, go back to our preset, and again, we're dealing with preset 13. So within our parameters section, we do have the ability to add a soft start. So this is going to allow us to have the tool go from a slow RPM to whatever RPM we have requested over a period of milliseconds, and that can be up to 300 milliseconds. So this is going to allow us to start, again, the tool slower, and it will ramp up to our RPM speed that we have programmed. Now, the other item that we can use is going to be our free reverse rotation, and that's done in our advanced tab. And if we go to preset 13, we can set that up right here. So we have our free reverse speed and our free reverse rotation. So we can set our speed here to say 75 RPMs and a rotation of 7/10 of a turn. And we want that, and that will go in the reverse direction, very similar to when you put a cap on a water bottle. You may spin it backwards first to find that first thread, and then go ahead and tighten it. This, in theory, is the same thing that we're doing. We're just turning the fastener in reverse, so it does have that ability to catch the first thread, and then it will go ahead and go into the fastening direction. And so let's go ahead and try this out on preset 13. Let's use this one here, and I'll take the fastener all the way out so we can go ahead and show what's happening. So drop that in, and we go in reverse, and then to our soft start, and then finally to our finishing torque and through that RPM. So that's how we can help to mitigate cross-threading because we want the items or the fastener to get in there correctly. Now, if I go ahead and let me make one adjustment here to our parameter. And I'm going to turn off the free speed and free RPM for the moment. And if we come back out, and if I were to simulate the cross-thread event, what we would do in this case, we have two different ways that we can handle this as well. And that's going to be done here in cooperation with error-proofing the fastening process. And so we're coming back in to the into the parameter menu here, and we are dealing with preset 13. And what we want to try to error-proof the assembly would be is if the operator does get a cross-thread event, we want the tool to be able to tell us that that has happened. And we can do that by utilizing the ability to monitor the amount of turn or angle that happens during the rotation. And by monitoring that, we can also tell the system to monitor the minimum amount of turn and the maximum amount of turn that we will allow for the assembly process. And so we know that the fastener itself is roughly 63 to 6400 degrees of rotation. We can set a maximum rotation here. Let's say 7,000 degrees of rotation, and we will find out that if we reach more than 7,000 degrees of rotation, we know that that fastener has stripped and that there is an error, and the system will tell us that there's an error. On the cross-thread side, what we can do is if that happens, that is going to happen right at the very beginning of the rundown. That fastener will bind up, and again, torque will be achieved. But if we put in a minimum amount of turn, let's say at least 3,000 degrees of rotation, which is quite a bit, for that, it will then give us an error if that happens. Again, giving us the ability to error-proof the assembly for this particular fastener because cross-threading might be an issue. And so if we come back out, and what I'll do is I'll go ahead and tighten a fastener that we've already tightened. And by doing that, that will give us an error, minimum angle error. And so that then alerts the operator, oh, we have an error. That was the minimum amount, which would be associated with the cross-thread event. Now, if I were to simulate the actual stripping fastener, if we run the fastener again more than 7,000 degrees of rotation, we'll get an angle over error here. And so we are again helping to error proof this assembly process for this fastening to alert the operator to go ahead and correct that mistake right now before it becomes an issue down the line. Now, there are several other items that we can use to help in catching different errors. We do have the ability to add a torque limit percent. So if there is a reading outside of a known percentage that we're looking for, that system will generate an error. There are other errors that are built into it. So if we were using our angle monitoring, we want to make sure that the operator doesn't let go of the trigger before the operation is complete. So we have the ability to add a fasten stop error, which means just that if the operator does not complete the operation with the handle completely depressed, then the system will generate an error. And so there are a number of these within the DC system. Those items we can look at, and we do look at in other scenarios, but we'll move along with what we have here. And our final one is going to be to automate the assembly. And so this allows us to go ahead and create an assembly process for this piece. And by doing this, we can have different fasteners that have different torque values and different errors that we can be looking for, different possible different angles and those types of things. So what we can do is we can actually go into what would be considered our model mode or what would be our assembly mode. And then we can go ahead and create what that would look like. So let's go into our controller here, and we're going to turn our model mode on. And if we come back out, you'll see that we're now in our model mode. If I go to select this, we would be selecting models instead of presets. And so models can be generated by the 15 different presets that we have available in the controller. So if we go back into our parameter menu and we come down here to our model, we now have 20 different operation steps that we can use for each model that will allow us to build our assembly. And so in this case, and for demonstration purposes, we'll make this pretty easy, but we can come in and we can select what type of operation we want for our model. And in this case, we're going to choose fastening. Next, we'll go ahead and choose which preset we want. And so in this case, we'll use preset number 1, and we're going to use a count of 1. So in this scenario, we're going to use preset 1 on one fastener. Our next, we'll use preset 2 and for one fastener. Our next one, we'll use preset 3 for one fastener. And then finally, we'll use preset 4 on another fastener for a count of 1. And we'll do this for these 4 fasteners here in this scenario that we are doing. And this is using just model 1. And so if we wanted to go and do another model, we could go to model 10 and not 70, model 10. And we could then go ahead and create a model for model number 10. So if we come back out, what you'll see on the screen here now is that we have model 1. This is preset and our first item here. So if I come to our fastener, we have our RPM speed, and then we also have our torque that we were looking to achieve. And I must have made the error here. And so now we're at preset 1, fastening 1. If we go ahead and run this down, now you'll see after it immediately reaches its, so we now have an error that we have reached the over torque for this fastener because of the joint characteristics here that we have set. So this gives us the opportunity to go ahead and correct this. If we come into our fastener here, we can look at what was going to be our RPM speed, and let's change this to 180 and it will come back out. And now we are within our tolerance. So we've now moved to our second step, which is our fastening step, and has now changed our torque and our RPM for our next fastening location. And again, I don't have the free speed and free RPM for these other fasteners, but now we have changed again to our next preset. So this allows the operator to basically move through the assembly as the controller is changing the parameters and other presets or characteristics for that fastening. Once the model is complete, we're alerted that it's complete, and then we can go ahead and move on to the next model or have a different model come in. We can also have these models started by a barcode scan or as a part comes in. So if you've got a mix of parts that come in, we can do that as well. So that's going to wrap things up for today with that, and that's going to lead us to our question and answer section. So if you have any questions, feel free to put those into the chat, and we'll do our best to answer them for you here. With that, Ashley, do we have any questions? So the transducerized tool basically has a sensor that is built into it that is monitoring the torque. So it has that ability to monitor and measure what's happening to the tool. There are other non-transducerized tools. DC control tool will basically convert the current draw from the tool to a torque value. So a lot of the same parameters can be used with a current control tool, but they're just not measuring the actual torque that's being provided. So again, the controller currently right now has the ability to store 15 different presets. So those could be 15 different torque values. They could be 15 different angle requirements for the same torque. It could be the number of fasteners that, or you can have parameters for different fastenings, different fasteners. So there are 15 different presets that can be made within the controller. Out of those 15 different presets, we can make 15 different models or 15 different assemblies sequences through that process. So 15 presets and the ability to have 15 different models. Sure can. There are two different types of fastening scenarios that we can use. What we showed today was primarily, excuse me, primarily torque control. We also have the ability to have angle control as well, where we can turn the fastener, or in this case, a tap. We can turn it a certain number of degrees, have it automatically reverse, or run through a hole and then have it automatically reverse after a certain amount of turn. But that can happen as well. And before we have any more questions, or if we do, I do realize that I did skip over one other automation part of the presentation. So do we have any more questions, Ashley? Okay, let me go back real quick, and that may spur a couple other questions as well. So right now, what you'll see, I haven't had this connected to the controller, but this is one of our bit socket trays, and so this can be used as another automation device that allows the actual bit to tell the operator which fastener or which preset to use. So let me go ahead and plug it in. And so again, so depending on the fastener that the operator might be using, if they pull that bit that is needed to be used, the system will automatically change to that that preset. So let me go ahead and come back out, and we'll change our controller back into preset mode. And so currently right now, I have pulled this bit, which is associated with preset 2. Then I can go ahead and use this bit on this fastener. For this fastener here, I needed to use this bit. That will go ahead and automatically change the preset up here to preset 1. If I pop that back in, you can see that the system is now locked. So there's no power to the tool right now because I don't have any bit selected. If I pull the third bit, it changes it to preset 2. It moves our status of the tool to OK. If I happen to have 2 bits pulled, it will go ahead and lock the system. Because we don't have the right bit pulled, we can drop this back in here, and now we're dealing with preset 3. So this is another way that we can use to eliminate a manual process for the operator to go in and change a preset that might be needed. We could also go the other direction with this, where we can tell the controller can tell the bit socket tray to go ahead and use a specific bit. If that bit is not used, then the system again will be locked, and the operation will not allow to be used. So again, this is another piece of equipment that will allow us to add that process control in there with the automation workflow. So sorry about that. Let's go back to our questions. So you can go back. The issue is going to be then it may throw off the count of that, but you can advance and go back for that through the process. All right. I want to thank you very much for joining us today. And I hope that you've learned something, and we look forward to seeing you again in our next video, or excuse me, in our next webinar. Thanks so much. Have a great day.